This is Professor Bittinger. In this short video lecture, we are going to look at how economic tools can be used to promote sustainability. In the first slide, there are three bulleted items that are considered to be tools that can help solve or deal with environmental problems. The first bullet refers to full cost pricing, which was defined in an earlier video lecture. Direct or market pricing usually ignores the hidden cost of harm to the environment and human health. If we were to include the hidden costs to the environment in the price of the good or product, it would actually cause that price to increase. Full cost pricing would reduce resource waste, pollution, environmental degradation, and improve human health, as well as support the principles of sustainability. The ways in which it would do this is that companies that are producing goods that have impact to the environment would need to make changes to produce them in a different manner in order to maintain the market price without it increasing as part of including the hidden costs. This is not a widely used concept, as producers of goods that do have impact to the environment oppose it. They oppose it because it would cause their cost to increase, and they recognize the fact that increased costs may impact the sales from the consumers. The other reason full cost pricing is not widely used is because currently government subsidizes businesses that do impact the environment, and government does provide tax benefits to some of these businesses as well. A different approach to this would be providing subsidies and tax benefits to those companies that utilize sustainable production methods. A third economic tool to deal with environmental problems is creating a tax on any kind of pollution and creating a tax on wasted resources or waste generation. This would help people decrease the amount of waste that they generate, as well as help companies realize that impacting the environment needs to change through their processing in order to minimize the impact overall on the environment. Some businesses would be able to transform themselves into environmentally beneficial ones. So these three concepts are not too far-fetched from being implementable. This slide is similar to the first, so take a quick minute to read over it, and we will continue to the following slide. I've been discussing full cost pricing with you, and next I'd like to present a case study pertaining to coal mining in Pennsylvania and how that has impacted the environment with our streams and rivers, as well as our air quality and air pollution known as acid rain. Coal has been mined in Pennsylvania for 200 years. We rank 4th in the nation in annual coal production. Each year, the Pennsylvania Department of Environmental Protection, Bureau of Abandoned Mine Reclamation, receives more than 800 requests for assistance with abandoned mine problems. These abandoned mine problems dot the landscape in 45 out of 67 counties. The Pennsylvania state was left with an estimated 250,000 acres of unreclaimed surface mine land, 100 million cubic feet of burning coal refuse, and the threat of land subsidence from old underground mines. Drainage from these abandoned coal mines has contaminated more than 3,000 miles of streams. If you look at the map on your screen, this depicts those areas across Pennsylvania that have been impacted by acid mine drainage. The streams that are colored in red have no fish present in them because the pH level has been decreased by acid mine drainage and no fish can live there. The streams that are in a darkish green color have some fish in them, but there is acid mine drainage impact. Overall, the miles of streams with no fish are 1,714, with some fish 1,525 stream miles. This indicates that there's more than 3,200 stream miles that have been impacted in Pennsylvania by acid mine drainage. To put this into perspective, to drive from Pennsylvania to Wyoming is about 2,300 miles. So if we were to put from tip to tip all these streams that have been impacted by acid mine drainage, it would extend further than from Pennsylvania to Wyoming, over 3,200 miles. That's a lot of stream miles that have been impacted by this industry. It's estimated that we lose $67 million annually because these streams are void of fish. The estimated cost to restore these streams and damaged watersheds is about $15 billion. With current funding levels from different sources, Pennsylvania DEP estimates that it would take more than 60 years to eliminate just the high priority abandoned mine land hazards in Pennsylvania. Since 1978, a total of 1,000 reclamation projects has occurred involving coal mining lands. There has been about 21,000 acres that have been reclaimed for a total cost of over $270 million. Since 1992, the Bureau started documenting environmental enhancements, and they've done over 88 wetland treatment projects involving more than 125 acres. In addition, they've planted over 800 acres of trees, and they've installed 260 brush piles and stone piles to improve wildlife habitat. There's also been a total of 73,000 linear feet of stream channels that have been enhanced by the Bureau. That seems like a lot of streams, but it was in linear feet. Converting that to miles means 13 miles of streams have been enhanced as a result of the reclamation projects to fix some of the acid mine drainage that's going on in Pennsylvania. As of 1996, the Bureau of Abandoned Mine Land Reclamation has fixed the following hazards at over a cost of $243 million. They have basically been able to secure and make safe dangerous high walls in old abandoned coal mines that present a safety hazard to the community of over 85 miles in height at various mines. They've also been able to fix 28 miles of clogged streams and improve 42 dangerous impoundments. They have dealt with 200 portals or open mine tunnels, and they have dealt with over 2,000 acres of land subsidence and addressed over 800 acres of underground mine fires, and also dealt with 360 vertical openings. Again, this was at a large cost of over $240 million. And please recall that back in 1978, they spent about $270 million. So this is a large cost. Yet, one thing that I would like to draw your attention to is that coal is our energy source that we rely upon most. And the reason we rely upon it is because it's cheap. It's cheaper than any other energy resource at this point in time. This slide is just a few pictures of the impact from coal mining in Pennsylvania. In the top left corner is the Centralia mine fire that is known nationally for an underground mine fire that spread out of control and could not be contained, and the end result was that the entire community had to be relocated. This fire is still burning to this day. The picture on the top right is an old abandoned mine tunnel, which basically has been flooded by groundwater, and now that groundwater flows out of the tunnel onto the land surface and convenes with another stream a little distance away from this tunnel. As you can tell, the stream is orangish in color, which is an indication that there is acid mine drainage happening at this location. Such a location causes a distinct safety hazard to the community. In the bottom left corner is a small stream, which you can tell by the orange color, this has acid mine drainage as well. And in the bottom right corner is an old abandoned strip mine that was mined for coal. And this is the Bear Valley Strip Mine, which is actually being used as an educational tour visit for many colleges where students are studying geology. They use this as a tour stop to understand how underground strip mining occurs, as well as the environmental impact associated with it. Most streams have a pH between 6 and 8 on the pH scale, 7 being neutral. On your slide to the right, you're going to see a couple columns with different pH levels. All these pHs range from slightly acidic at a pH of 6.5 to moderately acidic at a pH of 4.0. Acid mine drainage will contribute to a stream becoming more acidic. In addition, acid rain can contribute to this as well. Both acid mine drainage and acid rain stem from the burning of coal, and we'll get into those details more on the next couple of slides. Organisms have different acid tolerances. The young are less tolerant of low pH. In fact, at a pH of 5, most fish eggs cannot hatch. Frogs can tolerate water that is more acidic, as indicated in the chart on your screen. They can survive in environments with a pH as low as 4.0. However, trout need to have a pH greater than 5.0 to survive. Even though frogs may tolerate higher levels of acidity, their food supply, such as the mayfly, may not. As indicated on the chart, the mayfly likes to live in environments with a pH of 5.5 or higher. If the mayflies are not present, this then impacts the food supply for the frogs and essentially could decrease the biodiversity of frogs as well. I mentioned acid rain in the previous slide. This slide provides a diagram depicting how acid rain occurs. The two primary components of acid rain are sulfur oxides and nitrogen oxides, or SOx and NOx. The diagram depicts a coal-burning power plant that emits sulfur dioxide and nitrogen oxide from its smokestacks. That sulfur dioxide will react with water vapor and convert to sulfuric acid. The nitrogen dioxide will react with water vapor and convert to nitric acid. These acids will condense in the atmosphere and fall to the earth as rain, snow, or even potentially dust particulate matter, all known as acid deposition. This slide helps us better understand where the NOx and SOx are coming from. Let's look at the sulfur dioxide pie chart on the left side of the screen. This diagram shows that 2/3 of the sulfur dioxide emissions comes from utilities, presumably coal-burning power plants. This is a well-structured, compact target for regulation, and the Clean Air Act has targeted coal-burning power plants to reduce their emissions of sulfur dioxide. On the right side of your screen is a pie chart for nitrogen oxides. The largest individual sector that contributes nitrogen oxides into the atmosphere is transportation, mostly automobiles. This is a highly dispersed source of nitrogen oxides, and it's difficult to regulate, unlike coal-burning power plants. However, looking at the pie chart on the right, the second largest sector for nitrogen oxide emissions is again utilities. So both of these pie charts are depicting that the primary source of sulfur dioxide and nitrogen dioxide are utilities and transportation. This diagram displays the annual nitrogen oxide emission levels and the annual sulfur dioxide emission levels across the United States between 1990 and the year 2013. There are bar charts presented for each state for each compound. The blue bar chart indicates the amount of emissions from 1990. The yellow bar chart indicates the amount of emissions from 2013. In 1970, our first federal regulation to protect air quality was passed and is called the Clean Air Act. This act was amended in 1990 to implement more strict environmental controls on utility emission stacks, i.e. coal-burning power plants. In looking at these data charts, there is a distinct evidence that the regulation amendment of 1990 had a definite impact on decreasing the amount of emissions on a per state basis for nitrogen oxides and sulfur dioxides. The largest emitter of nitrogen oxide in 1990 was found in Ohio. In 1990, over 534,000 tons of nitrogen oxides were emitted in Ohio. Similarly, Ohio was the largest emitter for sulfur dioxides in 1990 as well, with 2.2 million tons. Pennsylvania was not far behind Ohio in their emissions in 1990 as you look at the bar charts. The good news that this graphic shows is that the yellow bar charts representing the 2013 emissions for nitrogen oxide and sulfur dioxide are much lower than what those emissions were back in 1990. So we have definitely seen an improvement in decreasing the amount of nitrogen oxides and sulfur dioxides that are emitted into the atmosphere since 1990. This slide provides some pictures of the effects of acid rain. The sulfuric acid and the nitric acid can damage monuments as well as cars. In addition, nitrogen oxides will react with sunlight to create photochemical smog, which is depicted on the right side of your screen. And then nitrogen oxides and sulfur dioxide create sulfuric acid droplets that cause damage to vegetation. And it's pictured in the center how various areas of trees throughout the forest have been damaged by acid rain. Finally, there has been a connection between emissions of nitrogen oxides and sulfur oxides with respiratory ailments, health problems, and even cancer. Acid rain has caused damage to trees at higher elevations in various areas of the United States. Specifically, the Appalachian Mountains and the Adirondack Mountains have shown the greatest signs of impact. That's partially because most of the coal-burning power plants that contribute to acid rain are found along the eastern coast. Direct effects of acid rain on vegetation include the leaching of calcium from the tree's leaves and needles. An indirect effect is that acid rain can actually change the underlying soil chemistry and deplete nutrients out of the soil such as calcium and magnesium. This then impacts the nutrient uptake of the trees, and obviously it's less than what it used to be, and it can impact the health of the tree. Acid rain also helps to leach aluminum, lead, cadmium, and mercury out of the soils and make them accessible to the root systems of trees. These are toxic to the trees. As a result, trees will die as they become more vulnerable to disease and in various environmental stresses. So, when talking about nitrogen oxide and sulfur oxide emissions, it's important to have an understanding of the history of the laws and programs that have been put in place to protect air quality. In 1967, an Air Quality Act was passed that makes states responsible for adopting and enforcing pollution control standards. Basically, it was delegated down to the states for them to do something. Due to a lack of commitment at individual state levels, the federal government then passed the Clean Air Act in 1970, and this law was revised in 1977 as well as 1990 and more recently as well. The Clean Air Act authorized EPA to set forth national ambient air quality standards and to set goals to achieve those national ambient air quality standards by the year 1975. This law regulates air emissions and focuses on reducing air pollutants. A special program called the Acid Rain Program was established under the Clean Air Act to achieve significant environmental and public health benefits through the reductions of emissions of sulfur dioxide and nitrogen oxide. The Clean Air Act did use an economic tool known as a market-based cap and trade approach to deal with the sulfur dioxide emissions. they set a permanent cap on the total amount of SO2 that could be emitted by a power plant nationwide. As a result, cap and trade started to happen with these coal-burning power plants. The initial phase of this market-based cap and trade approach occurred in 1995. A second phase occurred in the year 2000. This resulted in further reduction of sulfur dioxide emissions from big coal-burning power plants. Some smaller plants were also included with these requirements. Total SO2 or sulfur dioxide emissions are permanently limited to the level set by the 1990 Clean Air Act. About 50% of the levels emitted in 1980. Stiff penalties or fines for the plants were put into place for those facilities that release more pollutants than are covered by their allowances. In addition, this law required that each facility would have to install a computerized continuous emission monitoring system to keep track of how much sulfur dioxide and nitrogen oxide the plant's individual units were releasing into the air. Power plant operators had to keep track of this information on an hourly basis and report it to the EPA electronically 4 times each year. This data was reviewed and verified that the power plants were meeting their required limits for sulfur dioxide and nitrogen dioxide. In 2005, the Clean Air Interstate Rule was created. It basically was called the Good Neighbor Act, and it covered 27 eastern states and the District of Columbia. It focused on these states because these were the states where coal mining and coal power plants were the most abundant. In 2011, the Cross-State Air Pollution Rule replaced the CARE Act, and it focuses on how air pollution does not abide by political boundaries and how to address situations where the national ambient air quality standards in one state are being exceeded not because of what's happening in that state, but because of the emissions that are occurring in an adjacent state, and those air pollutants are moving through wind towards the state that's not meeting the air quality requirements. So it's a law that allows some flexibility in addressing non-compliance issues in relation to interstate pollution problems. Currently, the burning of coal in Pennsylvania contributes significantly to fine particle pollution in the District of Columbia and the following 10 states: Maryland, West Virginia, North Carolina, Michigan, Ohio, Delaware, Georgia, Connecticut, New York, and New Jersey. Air pollution does not stop at the state boundary. Hence, the Cross-State Air Pollution Rule that replaced the CARE law has helped Pennsylvania sources reduce their emissions in order to benefit these different states. The diagram on the slide in front of you provides data that documents the success. The top table indicates that sulfur dioxide emissions in Pennsylvania have been reduced by over 86%, or 835,000 tons. If you look at the data for the Pennsylvania SO2 emissions without CARE, they were projected to be 967 in the year 2003, 1,000 tons, up to 851,000 tons in 2015. With the implementation of CARE, those SO2 emissions were decreased to 235,000 tons in 2010 and subsequently 132,000 tons in the year 2015. So we've definitely seen an improvement in the decrease of sulfur dioxide emissions as a result of this law that was passed. Similarly, you'll see the same results for nitrogen oxides. Pennsylvania has reduced their emissions of nitrogen oxides by over 97,000 tons, or 56% from the 2003 levels. The diagrams on the screen in front of you depict acid rain throughout time. The one in the top left is 1999 data, and the bottom left is 2009 data, and on the side here to the right is 2011 data. The green indicates a pH of greater than 5.3. It's still considered acidic, but slightly acidic. What we're looking at is the areas that have the reddish orange to light orange colors. Those are definitely indicators of acid rain from the samples that were collected in those regions. In 1999, if you look at the state of Pennsylvania, it appears that the average pH of rain was about 4.3. In 2009, if you look at the state of Pennsylvania, the pH increased to about 4.7. That means it's becoming less acidic. If you look at the map of 2011, it looks like the pH is more in the range of 5.0. So we're seeing a trend of improved air quality and decreasing of acid rain. Notice that the large orange area in the figure in the top left for the 1999 data set is much larger in extent of depicting the amount of acid rain as opposed to that in the 2011 map that's presented to the right side of your screen. The Energy Information Administration was tasked with compiling the cost associated with dealing with air emissions that cause acid rain. This entity estimates that the annual cost is $836 million. This agency also projected an annual cost for the sulfur dioxide emissions program since 2000 as being equal to about $3 billion annually. Hence, there's a lot of cost associated with burning coal that's as a result of the impact to the environment. Again, bringing back the point that if we had a full cost approach associated with the product of coal, coal would not be as cheap as what it is now, and we likely wouldn't be reliant upon it as much as we are now. This map depicts different areas that have sensitive soils where acid rain and even acid mine drainage can cause further detriment. The areas shaded in red depict current problem areas, including lakes and rivers. The areas shaded in yellow depict potential problem areas because of air pollution and emissions that lead to acid rain. The areas depicted in green depict potential problem areas because they have sensitive soils in those regions. An economic tool that can help decrease the impact on the environment from coal burning power plants and other industries is to use subsidies that can be used to encourage companies to move towards environmental sustainability. Currently, subsidies and tax breaks encourage degrading the environment. These should be eliminated. In addition, there is political interests that stand in the way of making some of these changes. In other words, harmful subsidies continue to remain while beneficial ones are less likely to be passed to help the environment. Another economic way of minimizing emissions from coal burning power plants and industries that cause air pollution is to tax the pollution and the waste instead of wages and profits. Green taxes can be applied to those who produce large amounts of pollution and hazardous waste. This would be a phased-in approach where it increases over a period of time. In addition, reducing other taxes to equal increase in green taxes, which result in no net tax increase. This provides a safety net for lower income populations. Many countries have such taxes. So this is a diagram depicting the advantages and the trade disadvantages of environmental taxes. One advantage is it helps bring about the concept of full cost pricing. It encourages businesses to develop environmentally friendly technologies as well as incorporate those technologies in the production of their goods. It's an easily administered tax by the tax agencies. Disadvantages are that lower income groups could be penalized unless safety nets are provided. Also, it is hard to determine the optimal level for taxes and fees, and if it is set too low, wealthy polluters of big corporations could just absorb the tax as cost and continue to release emissions into the atmosphere.